तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome to lecture number 33 in our ongoing series on mechanical measurements. In this lecture I am going to start looking at the measurement of volume R and mass flow rate of fluids, both liquids and gases. We will look at different types of flow measuring devices. Broadly they can be classified as either variable area type, the drag effect type and the positive displacement type. So, the present lecture will more or less confine itself to the discussion of variable area type flow measuring devices, and in the next slide I have shown what we are going to do in the present lecture. So, we look at the principle of operation of variable area flow meters. Basically what we do in the variable area flow meter is to deliberately create a change in the area of the duct through which the fluid is flowing, mostly circular pipes. We deliberately introduce a change in the area. Because of the change in the area, the velocity of the fluid is going to undergo a change. Because of the change in the velocity, there will be a change in the static pressure, and we measure the static pressure and relate it to the flow which is being measured, or the flow rate which is being measured. Of course, we will have two different cases, one incompressible corresponding to either liquids or gases flowing at very low velocities, and if the velocities are not very small or moderately high, then some compressibility effects may be important in the case of gas flows. So, we will look at the basic equations which describe the variable area flow meters, and then we will discuss three types of variable area flow meters which are normally employed: the orifice plate, the nozzle and the venturi. And of course, we will round off the treatment if time permits in this lecture with example number 38, which will discuss a problem involving these three devices. Let me go to the board and look at the principle of operation of a variable area flow meter device. Variable area flow meter. We will look at the principle of operation of such a meter. Basically what we do is we assume that the flow is that of an ideal fluid, that means there is no viscosity, and then we look at the flow through a tube of variable cross section or variable area for the flow, and assume that the flow is one dimensional and steady. So, let me just indicate what we are trying to do. We will have a deliberately introduce some change in area. So, let us assume that this is the region in which we are interested. We will call this as station 1, we will call this as station 2, and we shall assume for the present that the flow is entering with the velocity u1 and the area of cross section is a1, and at section 2 the values are going to be u2 and the area of cross section a2. So, we are assuming one dimensional flow, which means that the velocity is a function only of coordinate x. So, u is a function of x only. The velocity is supposed to be uniform across the cross section, this cross section as well as this cross section, and we will assume that viscous effects are very negligible. Of course, we will introduce correction to account for viscous effects later on, and we will assume that the flow is steady. So, the equations which govern the flow of a fluid through a variable area duct or variable area cross section device like this are the equation of continuity. And to start with, let us assume that the flow is incompressible. That means that the density is constant, and therefore, equation of continuity or mass conservation equation requires that the volume also be conserved. So, there is no change in the volume, and therefore, we can say the volume flow rate, which is constant across the two sections, is given by u1 a1 is the volume flow rate across the section 1 must be equal to u2 a2 across the section 2. So, we can call this as equation 1, which is actually conservation of volume, because density is constant, conservation of mass is satisfied once the conservation of volume is satisfied. The second equation I am going to use is the momentum equation, which can be actually integrated, assuming that the velocity is constant across the cross section. We can integrate the momentum equation, which is nothing but a statement of conservation of mass, conservation of momentum, in the following form. So, P1 by rho plus u1 squared by 2 is equal to P2 by rho plus u2 squared by 2. This is equation number 2. So, we have two equations, the equation of conservation of mass, which became equation of conservation of volume flow rate, and the second is equation of momentum conservation, which on integration actually gives you this equation, assuming that the velocity is uniform across the cross section, and it is a function only of the location along the variable cross sectional area duct. From equation 1, I can do the following. You remember u2 a2 equal to un a1, and therefore, I can say u2 is u1 into a1 divided by a2. So, I can substitute into equation 2. So, this I am going to put in here, and what I will get is P1 minus P2 by rho. I am just taking P2 by rho to the other side, will be equal to u2 squared minus u1 squared by 2, and u2 I am going to substitute this becomes u1 squared into a1 by a2 whole squared minus u1 squared divided by 2, which will be the same as u1 squared by 2 is common into a1 by a2 whole squared minus 1. So, this is the equation obtained by combining equation 1 and 2. I get this equation, and let us now look at the volume flow rate, which is nothing but Q equal to either u1 a1, which is also equal to u2 a2, and I will use the expression for u1 from equation number 3. If you go back to the previous, you can see here u1 from equation 3 I can write u1, solve for u1 in terms of the other quantities and substitute to get a1 multiplied by u1 is nothing but square root of 2 into p1 minus p2 by rho, this is from equation number 3, multiplied by 1 over square root of a1 divided by a2 whole squared minus 1. This can also be written down as a1, instead of a1 I will say a2 multiplied by a1 by a2, and then I will adjust it with the denominator here. Therefore, this also can be written as a2 square root of 2 delta p by rho p1 minus p2 I am going to call as delta p, and a1, instead of a1 I am putting a2 here. So, I will adjust it by saying that this is equal to 1 minus a2 by a1 whole square. So, q equal to a2 square root of 2 delta p by rho 1 over square root of 1 minus a2 by a1 whole squared. This is the formula I am going to get. So, in a flow measuring device based on variable area principle, I am going to measure this. Delta p is measured. So, we will say delta p is measured, the ratio a2 by a1 is also measured, because I know the change in the area. So, I know what the area is at a1 at section number 1, and I know what the area is at section number 2. The assumption is that a2 is less than a1. The section 1 is the larger area and the a2 is the smaller area. Okay. So, I am going to basically use the measured pressure difference delta p and the value of a2 by a1, which characterizes the variable area device, and use this equation, which I will call it as equation number 4, as the basis for the measurement of the volumetric flow rate, assuming of course that the fluid is incompressible, or if the fluid is of gas, for example, the velocity is small compared to the speed of sound, such that the incompressibility assumption is valid. We have already seen this earlier in the case of pitot tube, also we have seen that. In order to make this equation 4 valid for a real fluid flowing through the variable area device, we can introduce a coefficient of discharge. So, what I will do is I will simply multiply this by C, a coefficient which is chosen such that the volumetric flow rate, actual volumetric flow rate is actually given by not by the ideal expression, this we will call as the ideal expression, multiplied by some coefficient which is to adjust for the non-idealness of the flow. Before we go to take a look at this, let me just clarify some points. In the writing the equation, I wrote down the pressure as P1 here. I also wrote the pressure as P2 here. The question is, what we are going to do in a practice is to measure the pressure at the wall, and here we are going to measure the pressure P2 at the wall. Okay. If there is some viscous effect, the viscous effect is going to be confined to region close to the boundary. So, viscous effect will be confined to the boundary. It can be shown from fluid mechanics principles that the pressure which is measured at the wall is equal to the pressure just outside the boundary layer, which is formed next to the boundary. and therefore, the pressure you measure here is exactly the same as the pressure in the bulk of the fluid. So, that is the basic assumption which is made in the use of the variable area device for the measurement of volumetric flow rate. So, I will say C is the coefficient of discharge, A2 is the area of cross section of the smaller cross section, delta P is the pressure difference between the section 1 and section 2 or station 1 and station 2, rho is the density of the fluid which is flowing through the duct, 1 over square root of 1 minus A2 by A1 whole squared. This parameter is usually referred to as the parameter m, or it is also called the velocity of approach factor. Why is it called velocity of approach factor? It is very simple. If A2 is very small compared to A1, we can actually neglect that term. If A2 is very small compared to A1, we can neglect that term. That means that the velocity at section 2 is much larger than the velocity at section 1, and therefore, if we are not neglecting the term, that means that A2 is not much smaller than A1, there will be, we are taking into account that there is a small velocity in the larger area section, and we are accounting for that. Therefore, it is called the velocity of approach factor. So, if you call it as m, this is C, I will rewrite the equation in slightly different form. So, I will say Q equal to C into m into A2 multiplied by square root of 2 delta P by rho, and this is the coefficient of discharge, and this quantity C into m, the product of the coefficient of discharge and the velocity of approach factor, is referred to as the flow coefficient. Flow coefficient, which is usually given the symbol capital K. So, we can also write this as K A2 square root of 2 delta P by. So, we can call this I think equation number 6. We can also do the following. For compressible flow, for the case of compressible flow, actually what we are talking about is flow velocities not too small compared to the velocity of sound, so that some amount of compressibility effects need to be taken into account. In that case, we will introduce another parameter, introduce a parameter called y, which is called the expansion factor. So, that equation 6 can be rewritten with a factor y here. I am just going to put the value of y there, and I will also put the y here. This y is going to account for the small amount of compressible effect which may be present, because the velocity is not very small as compared to the speed of sound, in which case of course you would use the incompressible flow assumption, but small amount of compressibility is there, that can be accounted for by the factor y. Of course, later I will discuss about what this y is, how it is obtained, and normally what is done and so on, that we will come back to later. But basically the variable area flow meter, the operation of that depends on equation number 6. So, with this background, let us go back to the slide and look at what are the different types of variable area type meters which are used. I have labeled here orifice plate, the nozzle and the venturi, and in fact how do they look. How do we create the variable area here? I am actually having a tube of diameter capital D, and the flow is taking place from this side. I have identified an obstruction which is called the variable area device, has an obstruction which is in the form of an orifice with smaller diameter d, this d is less than capital D. So, the smallest area as far as physical area in this case is capital D represents the area in the pipe and small d represents the orifice, the corresponding to D, the corresponding area will be the orifice area. And what we have done is deliberately we have changed, we have introduced a area change here by introducing a small plate with a hole in it. Okay. So, if the flow which is coming here, because it has to pass through the small hole, it is going to accelerate when it comes towards the hole, and therefore, how does it accelerate? The pressure is converted to, pressure energy is converted to the kinetic energy, because kinetic energy is increasing, it comes from the pressure. The potential energy is converted to kinetic energy, therefore, the velocity is larger here as compared to here, and that is what happens. Now, we can choose two locations 1 and 2. In this case, I have taken one upstream of the, this is upstream of the orifice, usually 1 diameter away from the orifice, ahead of the orifice, and the second one I can choose very close to the orifice, like what I have done. There are different ways of doing it, which we will come to a little later on. So, what I will do is I will measure the pressure difference between P1 and P2 and use that equation which we had, equation number 6, which gives the volumetric flow rate in terms of the measured pressures and the known diameter or the corresponding areas, we can measure the volumetric flow rate. So, the schematic of an orifice is simply showing that there is a small area due to an orifice which is introduced in the pipeline, so that the flow accelerates, the pressure changes, we measure the pressure difference and then we relate it to the volumetric flow rate. The second arrangement, which is much better, we will see later why it is much better, is to have a nozzle which is specifically shaped so that the streamlines are going to follow a certain contour, and in this case we are going to have much better coefficient of discharge, and we will also see later that the pressure loss due to this flow nozzle is much smaller than due to the orifice plate. So, here again what you see is that I am measuring the pressure at section 1 and the pressure at section 2, which may be at the exit of the nozzle or some other location which is specified, and we measure the pressure difference and again related to the volumetric flow rate. Again I have used the same symbol, capital D for the pipe diameter and small d for the smallest section of the nozzle. This is the exit section, is the smallest section. The third arrangement, which is one of the best way of doing it, is to have a venturi which is a converging diverging nozzle. So, it starts converging from D to a small diameter D, and again it starts diverging and it goes back to the original diameter of the thing. Of course, the disadvantage of the venturi, if you want to refer to it as a disadvantage, is that it requires a long length for the measuring device. The venturi itself is a very long, from here to here it is a fairly long thing, where compared to either the orifice plate, which is just a small plate with a hole in it, or you take the nozzle, it is a short thing, whereas here it is a very long thing. So, the disadvantage of the venturi is requires a long length for installation. And let us look at what is happening. I have just schematically shown the change of the pressure or the variation of the pressure along the direction of flow. The direction of flow is from left to right as is shown here, and the pressure is uniform till it comes to the variable area section and it starts reducing, and at section 2 it has got the minimum value because the velocity is highest here, the pressure has come to the last, and in the diverging section the velocity again starts decreasing and the pressure will start increasing. But you will see that the pressure here is slightly different from the pressure here, because the pressure does not come back to the original value, but there is a slight difference between the P1 and the P at the exit. This difference between this pressure and this pressure is called the irrecoverable pressure loss, and later we will see how it varies with different flow metering devices, the venturi, the nozzle and the orifice plate. We will see how it is called, but essentially any variable area device will have a pressure variation like this. To some extent pressure recovery will take place, but the pressure will always be lower than the pressure upstream of the flow measuring device, because there is a what is called the so called irrecoverable pressure loss. So, let us look at the three devices in some more detail. The orifice plate. The orifice plate is essentially a tube with a small obstruction like this. I have just this is a schematic, and I have indicated three different ways of measuring the delta P, locating the pressure taps for P1 and P2. If I look at this, these are called the flange taps. Why is it called flange tap? Because the orifice plate is going to be assembled as a thin sheet of material with a small hole in the center, which is going to be held between two flanges, and the two pressure taps are very close to the flanges. So, they are called essentially flange taps. This is 1 inch and 1 inch. If you want, you can take it as 2.5 centimeters and 2.5 centimeters in the case of the SI system. So, this is one arrangement. You measure the delta P between the two flange taps as is shown. The second one is referred to as the DD/2 taps. The first tap, the upstream tap is at a distance of d from the orifice, and the second tap is d/2 from the orifice as is shown here, d and d/2 taps. So, this is one and this is two taps. The third arrangement which can be done is called the corner taps, and in this case the two taps are right adjacent to the flange, right adjacent to the orifice plate on the two sides of the plate. So, there are three different ways of using the taps for the pressure measurement. So, what is this tap I am talking about? It is a small diameter hole, normally 1 to 3 millimeters in diameter, and to which the one of the manometer legs is connected and the other manometer leg is connected to this. That is essentially what it is. If you do not want to use a manometer because it is not convenient or it is not possible to use because the pressure difference is too small, then you can use two pressure transducers or one differential pressure transducer, and this tap will be communicating to one side of the differential pressure transducer, and this tap will correspondingly go to the other side of the differential pressure transducer. And in fact, we have already looked at the differential pressure transducers earlier on. So, the choice of whether you are going to use a manometer or a differential transducer measure differential pressure transducer depends on the maximum pressure difference you are going to encounter in a particular application. Of course, it depends on the velocity, the fluid and so on. So, depending on the range of the pressure difference which you are going to get, you can choose the proper pressure measuring device, either a manometer, or you can also have, for example, we have already seen an inclined tube manometer if the pressure drop is very small, and we can choose the manometric liquid choose suitably so that it gives you a large reading and so on and so forth. This is already something which we have seen. The third point which I want to discuss here is, depending on the location of the taps, I will refer to this length as L1 and this length as L2. L1 is the length distance from the orifice plate to the upstream tap, and L1 L2 dash is the distance from this face to the other tap, okay, the second tap. The coefficient of discharge has been measured for standard orifices, and it depends on two factors. One, it depends on what is called beta. Beta is the ratio of the diameter of the orifice to the diameter of the pipe, d by lowercase d divided by capital D, that is your beta. In fact, you can see here d and d, that ratio is the here, this d divided by capital D is called the beta. The beta is the symbol which is used for all the three different types of flow meters, the orifice plate, the nozzle as well as the venturi. So, it depends on beta. Secondly, it depends on the Reynolds number of the fluid flow within the pipe in this portion. So, what is the problem with this equation? This is incidentally called the Stolz equation. Stolz is the name of the person, Stolz equation. The equation says that the coefficient of discharge is 0.59959, this is the dominant term, plus some contributions due to the value of beta, then the L1, L2 etc., and then we have a term which depends on the Reynolds number. Because Reynolds number is not known, when you want to measure the flow rate, we do not know the velocity, therefore, we do not know the Reynolds number. So, this may require a little bit of iterative procedure, because Reynolds number has to be guessed or taken some value and then find out the velocity and then find out the Reynolds number again and so on. That will require some little bit of iterative solution. For example, L1 is equal to 0.4333, L1 is nothing but the ratio of this distance to the diameter of the pipe. It is a non-dimensional parameter. L1 for example could be 0.433, if it is greater than 0.4333, you have to use in this term, instead of 0.09, you use 0.039 in this term, and beta is d by d, and this will give you a value of C. Normally what we do in the case of an orifice plate is we can start with the value of C equal to 0.6 as a starting value, because we will see later that the value of C is close to that value, and then correct after evaluating the from the pressure drop data, after evaluating the velocity, then you come back here, calculate the Reynolds number based on the evaluated velocity, and then correct for the C value by using this equation, the Stolz equation, and maybe one or two iterations will be sufficient for this purpose. In fact, what I have done is I have plotted the flow coefficient for an orifice with corner taps. Corner taps means L1 equal to L2 equal to 0. So, what I have here is the flow coefficient. If you remember, flow coefficient is nothing but the product of the coefficient of discharge and the approach velocity of approach factor. All I have done is I have taken the Stolz equation, evaluated the CD, multiplied by the k value and plotted it. For beta different values, beta equal to 0.5, 0.6, 0.7 and 0.75, and with the different values for the Reynolds number. So, what we see here is very interesting. The flow coefficient is almost constant for values of Reynolds number greater than about 10 to the power of 5. So, if in the particular installation the Reynolds number in the pipe is more than 10 to the power of 5, you can use a constant value for CD, and that is the advantage of that. Okay. Of course, the actual value of CD depends on beta. For different values of beta I have different values of flow coefficient, but they also show some kind of an asymptotic behavior, which means that for a Reynolds number greater than about 10 to the power of 5, 100,000 is 10 to the power of 5. These are more or less independent of the velocity or independent of the Reynolds number. Of course, the Reynolds number is calculated based on the velocity, the diameter of the pipe, and also the particular fluid which is flowing. Okay. So, the fluid property also is coming in to this by itself. The second type of device we can think of is called the ASME long radius nozzle. ASME is American Society for Mechanical Engineers, who have standardized the design. I will show the long radius nozzle in slightly more detail in the next sketch. Essentially what we have is a P1 upstream of the nozzle, this is the nozzle, P2 is upstream downstream of the nozzle, and for the ASME long radius nozzle the coefficient of discharge is given by 0.9965 minus a small quantity 6.53 beta to the power of 0.5 divided by Reynolds number to the power of 0.5. Again you see that C depends on Reynolds number and the value of beta, and the diameter of this I am talking about this diameter could be anywhere between 50 millimeters and 650 millimeters. We are talking about fairly large range of values for the diameter. 50 millimeters is a typical size met with in many engineering applications. 650 millimeters, for example, can be met with in large scale installations like water supply or gas flowing through a pipeline, natural gas flowing through gas pipeline and so on. You can have very large diameter pipes. Water supply is one example. So, if you go back to the sketch, you will see that the long radius nozzle can have values of beta between 0.2 and 0.8 and the Reynolds number between 10 to the power 4 and 10 to the power 7. Normally less than 10 to the power 4 we do not use any of these devices. In most applications the Reynolds number is certainly more than 10 to the power 4. Let me just digress a little bit and look at this 0.2 to 0.8. Why do we have such a large range of values for beta? If you go back to the equation which determines the flow rate from the delta P is actually created by the change in the area, and if the beta is small the change in area is larger and the delta P is larger. Therefore, in most applications where we want to use a variable area metering device for measuring velocity or flow rate, we must make sure that the delta P which you are going to obtain is large enough to be measured easily by using an available pressure measuring device. Therefore, depending on the application, depending on the velocities which are achieved in that particular thing, you may choose different values of beta or choose the appropriate value of beta such that the pressure difference is measurable and easily measurable at that. So, that is the reason why we have different values of beta, and you can choose anywhere between 0.2 and 0.8 for this particular case as I have indicated here, which is also true for other devices. Again I have shown the proportions of a long radius ASME nozzle. Essentially the nozzle consists of, this is the nozzle, what is shown here is the nozzle, the exit diameter is d, inlet diameter is d here, and the nozzle itself is contoured in the form of an elliptic part of an ellipse. From here to here it is a part of an ellipse with a major axis equal to d, this is the diameter d, this length is d, and the semi major axis will be 0.6d minus 0.5d multiplied by 2, because that will give you this plus this. Okay. So, this is the standard procedure for obtaining the long radius ASME nozzle, and the long radius ASME nozzle is recommended for beta between 0.45 and 0.8. These are the values between which this can be used. And what is important for us is only the inner contour, the outer contour is of no significance, and the pressure is measured upstream of this phase and close to this or some other phase depending on the particular design. So, the flow coefficient for long radius ASME nozzle is again shown here. If you remember, the flow coefficient is nothing but the product of the coefficient of discharge and the velocity of approach factor, and the velocity of approach factor is given by 1 over square root of 1 minus a2 by a1 whole squared. a2 by a1 is now d squared by d by d whole squared, because area is proportional to diameter square, and therefore actually the velocity of approach parameter is nothing but 1 over square root of 1 minus beta to the power 4. We can easily see that. So, if we choose a particular value of beta, the velocity of approach factor gets fixed, then the CD is going to determine the product of CD and M, CD and the velocity of approach factor, and therefore flow coefficient is nothing but the product of these two. And if you remember, the value of the CD for a nozzle is very close to unity. That means the value of the flow coefficient is almost close to the value of the velocity of approach factor itself. Of course, there is a small Reynolds number dependence, and of course asymptotically it will reach the value equal to m or very close to m. Okay. So, this is for the ASME nozzle. So, if you compare the orifice plate and the nozzle, orifice plate has a low value of flow coefficient And if you go back to equation number 6, which showed the dependence of Q versus the rest of the things, if the coefficient of discharge is smaller or the flow coefficient is smaller, it means that the delta P generated will be higher. Okay. So, the RF phase plate is going to give you a larger pressure drop or pressure difference or measurable pressure difference as compared to the nozzle in this case. Of course, we will see in a moment that in the case of Venturi also the same thing is possible or same thing holds. So, I have a proportions for a Venturi are given here. It consists of two sections, the converging section, then a landing or a flat region where the diameter is uniform equal to small d, and then it starts diverging again. The angle of convergence can be 21 plus or minus 2 degrees, this is the allowed values. The diverging section can have an angle of 5 degrees to 15 degrees, any angle can be chosen. So, if you choose a angle of 5 degrees, the length will be very large. If you take a 15 degree angle, it will be shorter. So, if you want a compact design for the Venturi, you go for a larger angle at the diverging section. If you do not mind having a very long Venturi, you can go for a 5 degree nozzle or any value between 5 degrees and 15 degrees. There is a, as I mentioned, there is a landing which is equal to diameter of the section here, and the second tap is positioned at d by 2. D by 2 is in the center of this flat portion, and the upstream tap is anywhere between d by 4 and 3d by 4, where d is the pipe diameter from the start of the converging section. Just before the converging section starts, you can have it anywhere between d by 4 and 3d by 4 as is indicated here. These are the proportions for a Venturi, standard Venturi, again ASME specification. So, the flow is taking place from this side. In fact, I have a small photograph of a Venturi meter which is commercially made, and it is taken from the website of Flow Systems Incorporated. They are the manufacturers of these Venturis, and you can see the Venturi meter is made very exceedingly well. You have the entry on the left side, the pressure tap is shown here, this is the pressure tap number 1, this is the pressure tap number 2, and you can see here there is a portion which is straight, which was without change in area, and it is in the middle of that, and there are two flanges, one at the beginning, one at the other end, and this entire thing is placed in between the, you make a small gap in the pipeline, introduce this in the pipeline for the flow measurement. So, these are these two pressure taps which are used for the measuring the delta P, which is related to the Q of the Venturi meter or the velocity flow, the flow rate. And in fact, the discharge coefficient of a Venturi shows some kind of variation like this. This is from measured data. So, the coefficient of discharge is a function of Reynolds number again, and you will see that it is starting with a fairly large value of about 0.96, and if the Reynolds number is more than about 2 into 10 to the power 5, it levels off at about 0.984 or so, 984. Okay. So, I do not have any ready-made formula for this, we can just use this graph and read off the value of the coefficient of discharge from this particular graph. So, now we will look at why we have 2 or 3 different types of meters when one of them can possibly be adequate. The pressure drop, if you remember, I mentioned that the pressure changes from the entry to the second section, it goes up, the pressure goes down because of the change in the velocity, and then afterward the flow is again going to expand and to fill the pipe. So, the pressure has to recover. The pressure recovery process is not the same in all the 3 cases. Let me just digress a little bit and show what happens to the pressure drop, pressure recovery. So, let us look at the pressure recovery. So, if I take a flow in a orifice plate, I will just indicate the orifice by a small hole here. The flow is taking place from this side. the flow is going to come like this and it will going to expand like this, and it forms some kind of a circulation pattern here, circulation pattern. And what happens in a circulation pattern? The flow is now, the kinetic energy is converted to the internal energy, and therefore some amount of pressure head is swallowed up by this activity, and therefore the pressure recovery here, pressure recovery is not good, pressure recovery is poor. Because of this flow which is generated, the flow separation, and then because of that. If you take a look at a venturi, this is a venturi, there is no flow separation, it goes nicely like this, follows the contour, the flow is not going to have any of these peculiar this kind of thing, the flow separation and then formation of a vortex there and so on is not there, and therefore there is no pressure, the pressure recovery is much better. So, we will say better pressure recovery. That means, if you choose the exit angle, that 5 degrees to 12 degrees or 15 degrees whatever we mentioned, if we choose within these limits, the pressure recovery is much better than in this case, because in this case there is a scope for the development of this separated flow and the circulating flow, which is going to dissipate some of the kinetic energy. And in fact, the nozzle also is a good device, because it is going to behave much better. And in fact, you can see that the orifice, the nozzle and the venturi, if you look at the pressure loss due to the installation, because of the total recovery is not possible. In the case of orifice, you can see that of course it is a function of beta. The smaller the beta, the worse is the pressure loss. As the beta becomes larger and larger, the pressure drop which is created is also small, and the amount of pressure drop which is not recovered is also small. So, let us look at how we have plotted here. Delta P is the differential pressure developed by the meter, this is P1 minus P2, and delta PL is the differential pressure irrecoverably lost. That means that this is the pressure at the exit of the device minus the upstream pressure minus the exit pressure. So, this is nothing but the pressure difference created by the device because of the acceleration of the flow in the converging section divided by the pressure drop across the pressure drop across the device from the inlet to the exit divided by the pressure difference created by the converging section. And you can see that for the orifice, almost even for beta equal to 0.8, almost 40% of the pressure drop is irrecoverable. That means 40% of the pressure drop which occurred in the converging section is going to be irrecoverably lost. Nozzle is slightly better, but you see that the venturi is the best, because even in the worst case of beta equal to 0.2, only about 30% of the value is going to be lost, and as you go to higher values of beta, it is asymptotically it is going to some 5 to 10% value. Therefore, the reason why we have 3 different types of devices, variable area type devices, is because orifice is not very good from the point of view of pressure loss due to installation, nozzle is slightly superior, but venturi is of course the best. But if you remember what I said earlier, orifice occupies the smallest length, nozzle is next to that, and of course venturi requires a large length for the installation. So, if you are particular about the length of the installation, then you can go for orifice, but then you have to sacrifice the pressure loss. The third the other point is that if you see, the nozzle and the venturi both have very high coefficient of discharge compared to orifice, and there is a plus point for the nozzle and the venturi. The coefficient of discharge is higher, and also the variation is small, whereas the orifice it is a very large variation, starts with 0.6, about 0.6. The third point which I should make is that RFA is very inexpensive. It requires a simply a small piece of a sheet of material in which you drill a hole, where a nozzle requires a contouring. It is very expensive, and the Venturi, of course, you saw the photograph. It is very well made and it requires a lot of machining and so on. Is most expensive. So the expense goes up in this direction, and as the expense goes up, the pressure loss also goes down. So you have to decide based on what is the requirement. Accordingly, you decide whether to use an orifice, nozzle or a Venturi. The cost wise also, orifice is the cheapest, nozzle is more expensive, and Venturi is the most expensive of the three different types of measuring devices. So let me just look at a simple problem. We want to use a Venturi in the measurement of air, flow of air at 5 bars and 25 degrees Celsius, and the maximum flow rate is given to be 1 kilogram per second, and the minimum flow rate is also mentioned as 0.3 kilogram per second, and we want to find out what is the size of the Venturi such that the pipe Reynolds number is not less than 100,000. In that case, we want to calculate the differential pressure developed across the Venturi if the beta is 0.6. So what I will do in this rest of the lecture, the amount of time we have, is just to work out some of the aspects of this problem and probably continue from there in the next lecture. So let us look at the problem. So the Venturi problem. This is example 38. We are given a beta is 0.6. It is nothing but your d by d is 0.6. The pressure is 5 bars and temperature is given as 25 degrees. So I will convert it to Kelvin. It is 298 Kelvin. So the air properties are evaluated at this pressure equal to 5 bars and 298 K. In fact, I have taken the pressure, the properties from a table of properties, and directly I will give the values. The value of the viscosity is 18.41 into 10 to the power of minus 6 kilogram per meter second, and the density at 5 bars is given by 5.844 kg per cubic meters. So the problem specifies that the pipe Reynolds number should be greater than or equal to 10 to the power of 5, and we will say that the minimum mass flow rate is 0.3 kg per second and the maximum possible is 1 kg per second. Okay. So if the Reynolds number has to be greater than or equal to 10 to the power of 5, this will be at m dot minimum. For the minimum mass flow rate, I must choose the Reynolds number such that it is equal to or greater than 10 to the power of 5. So that will be the limiting value. So if I limit the value, so if you remember, Reynolds number based on the diameter is given by 4 m dot minimum by pi d mu. So this is equal to, so 10 to the power of 5 equal to 4 into m dot is 0.3 kg per second divided by pi into d we do not know, that is what we have to determine. Mu is given by that 18.41 into 10 to the power of minus 6 value, and this gives you, solve for d, it comes to 0.207 meters, some 21 20 centimeters, 20.7 centimeter. And we are also given beta equal to d by d equal to 0.6, 0.6 is equal to d by d, therefore d is equal to 0.6 into 0.207 meters, and this value is 0.124 meter. So the Venturi meter has got an inner diameter at entry of 0.207 meters. The smallest cross section has a value of 0.124 meters. In fact, now I can calculate what is the delta P which is going to develop. For that, we know that Reynolds number is equal to 10 to the power 5 for the minimum value. The corresponding C value I can take from the graph which I showed earlier. So if you see 100,000, this is the value, and the value is corresponding to it something like 0.756 or so, 975,977. So we can take that value from here, from this graph. So because the Reynolds number is already given, I can simply take the value from that, and therefore this value of C is equal to 0.977 as I just now indicated. So if the value of C is given, I can calculate now m. The velocity of approach factor is 1 over square root of 1 minus beta to the power of 4. So 1 over square root of 1 minus 0.6 to the power of 4, and the value of m happens to be 1.072. So I use equation 6. Of course, with the assumption is that y equal to 1, there is no expansion factor, expansion is the compressibility effect is not there. Therefore, I can say delta P minimum by using that equation is m dot minimum divided by C m A at the throat, because second whole squared multiplied by 1 over 2 times rho. So I will just substitute the values. AAT is the throat area, which is given by pi d squared by 4, and that happens to be 0.012 square meters, capital D, that is pi into d squared lowercase d whole squared by 4. So this will be 0.3 divided by C is 0.977, 1.072 into 0.012 whole squared 1 over 2 into 5.844, that is the density, and this will be in so many pascals, and the value comes out to be 47.4 pascals. So the pressure drop which is measured comes to 47.4 pascals at the minimum of the flow rate. We will continue this problem in the next lecture, and what I want to do there is also to compare what happens if we replace the Venturi by a nozzle or by an orifice plate. What is going to happen? We will discuss that at the beginning of the next lecture. Thank you.